As mentioned before, there are actually two approaches for the actual pattern classification process. These can be either hidden Markov models or neural networks, and I will explain both approaches in the following. The hidden Markov model approach can best be dealt with if we first consider a discrete hidden Markov model. This hidden Markov model consists of a sequence of states, which you see here with the blue dots. And there are transitions between those states, or from one state to the same state. And each of those transitions is characterized by a so-called transition probability, which you see here. There's also the possibility to jump over one state, but there's never a possibility of going back to the previous state. There's a second type of probabilities, which are the so-called emission probabilities, and these are the probabilities that a certain state, when passing through it, emits a certain symbol. And this symbol can, for example, be a sound or a phoneme. Now, if you want to calculate the overall probability that this sequence of states has produced a certain sequence of symbols, we have to multiply the corresponding probabilities. That is, we have to multiply, starting from the first state, the probability that this state emits the first symbol, multiply with the probability of running through the next state, multiplying with the probability that that state produces the second symbol, multiplied with the probability of running through the third state, multiplied with the probability that this third state produces this symbol, multiplied with the probability of running to the fourth state, multiplied with the probability that this state produces the fourth symbol, multiplied with the probability of running to the fifth state, multiplied with the probability that this state produces this symbol. And this overall multiplication gives you the probability that this sequence of states has produced this sequence of symbols. As we as humans pronounce speech in slightly different ways, there's also the possibility to stay in a state, that is to pronounce a certain sound a little bit longer, and also to omit certain states, that is to not articulate particular parts or particular sounds in a word. This discrete hidden Markov model is already quite impressive. It's quite helpful for the second decoding state, but it does not consider any features which we need to extract from the speech signal in the first stage. This can be taken into account by the second type of hidden Markov model, which is a continuous or phoneme hidden Markov model. It works more or less the same way as the discrete hidden Markov model does. That is, we have states, which are described here with 1, 2, 3, and we have transition probabilities between the states. But now there's a fixed alignment between these states and a particular class of phonemes in the way that typically 3 states constitute one phoneme, in order to take into account the co-articulation, so the shaping from the previous sounds and from the subsequent sounds in the articulation of a particular word. What these states emit is now not a discrete symbol, but it's a continuous probability for a certain feature vector, which we have extracted in the first part of our speech recognition architecture. So the emission probability of this state, that this state produces this feature vector, is then a multivariate probability, because this feature vector contains a number of different components, and thus we need to have a multivariate, multidimensional model of the probability that this state emits this certain feature vector. So it's usually modeled with a multivariate Gaussian probability distribution function for each of the states. Now we can calculate the probability that this sequence of states emits a certain sequence of feature vectors by multiplying the emission probabilities that those states emit certain feature vectors multiplied with the transition probabilities between the states or from one state to itself, as we have calculated it with a discrete hidden Markov model. The hidden Markov model is just one way to calculate those probabilities. There's a second way, which is called the neural network. A neural network is in principle a very simple classifier, which is able to classify an input vector, an n-dimensional input vector, into an output which only consists of two classes, class A and B, or class +1 and -1. And the way this is done is illustrated in this formula. So the individual components of the feature vector are weighted with corresponding weighting coefficients, then summed up. There might be a bias subtracted here, and then a threshold function, this one here, is used in order to distinguish between the two classes. In the very simple two-dimensional case, we can imagine that this is just a two-dimensional plane which is separated into two classes by a straight line. And in three-dimensional case, this would correspond to a plane in a three-dimensional space and to a hyperplane in a general n-dimensional space. Now this classifier, this so-called single-layer perceptron, is only able to distinguish between two classes, but in speech recognition we have to deal with much more classes, namely the number of different phonemes or sounds in a particular language. In order to deal with that, we can organize perceptrons in multiple layers in such a way that the output of one layer constitutes an input component to the neurons on the next layer. So in this example, we have the input features here, and we have a number of perceptrons organized in two different so-called hidden layers in the middle, and then we have a number of phonemes in the output layer. This number of phonemes can correspond to the number of sounds, but because of binary coding of those, we may even deal with a smaller number of perceptrons on that particular output layer. Now, as you have seen, there are two approaches for the classification, either the hidden Markov model or the neural network with different layers. Both can be used in both of the stages of the classification process, which you have seen in the architecture of the automatic speech recognizer.